Okay, in chapter 13, we're going to talk about vector functions. For example, suppose you have a curve that's given parametrically, x equals f of t, y equals g of t, and z equals h of t. You could also describe a point on that curve by a position vector, r of t, where the components of r of t are the functions f, g, and h. We call that a vector valued function or a vector function. Think of it like this. If you have a curve here in R3, and you have a point on that curve, the position vector is given by r of t. So how would you find the position vector for the line that contains these 2 points? Well, as you know from the last chapter, to find the equation of a line, don't you need a point and the direction vector? So you can form the direction vector by subtracting the coordinates. And then you could even do what I usually do is go ahead and get the parametric equations for the line and then make them the components of the vector function. How about this? This is a little different. Suppose you want to find a vector function for the line segment from this point to this point. Well, what I'm going to do is actually find the equation of the line segment. When t equals 0, you're at this point. When t equals 1, you're at this point. It's not too hard. Think about it this way. R of t at t equals 0, notice at t equals 0, this is 1, so you're at the vector r0, and this vector is 0. And at t equal 1, this vector is 0, and this vector is r1. So at t equals 0, you're at r0, and at t equal 1, you're at r1. If you just look at the components of the vector, by the way, r0 would be the position vector whose terminal point is this point here, and r1 would be the position vector whose terminal point is 2, 1, negative 1. Anyway, so when you multiply r0 by 1 minus t and r1 by t and look at the components, you end up with this. So that would be just the line segment, okay? At 0, you're at the first point, and at 1, you're at the second. That's a nice way to do it. Okay, let's spend some time looking at some specific vector functions. Here we're in R2. This is a vector whose components are sine t and cosine t. So wouldn't that be moving around a circle? I have it in R3, but z would be 0. But anyway, t equals 0. Aren't you at the point 0, 1? 0 at x, y equals 1. So you're right here at t equals 0, and you're going to be moving counterclockwise, right? Anyway, compare that to this vector function. X is sine t, y is cosine t, and z is t. You've seen this one a lot, or you will see this one a lot. I use this a lot of times in class because it's so easy to draw. But x and y are moving around a circle. At t equals 0, you're right here at the point 0, 1, 0. And you're moving in a counterclockwise sense, but t is also changing, so it's like a spiral, a helix actually. How about this one? X is sine t, y is cosine t, z is 4. Notice though the z coordinate is always 4, so think of it as you're moving along 4 units up. You're flying in a circular pattern 4 units above the xy plane, aren't you? T equals 0, you're here, and you're moving counterclockwise. See if you can figure out what this is. Go ahead, hit the pause button, see if you can sketch this vector function. Okay, you know x and z are moving around a circle. Y is always 4. Did you get this? You should have gotten a circle where the y coordinate is always 4. At t equals 0, you're up on top here, and you're moving towards the y plane in a sense. All right, try this one. See if you can sketch this vector function. Okay, notice y is always 0, so that tells you you're in the I should say x. X is always 0, so you're in the yz plane. Isn't this the cosine function in the yz plane? So make sure you know x is 0. So this is just the cosine function, but it's in the zy plane, isn't it? Interesting, huh? Let's keep on going here. Let's try some more. This is a good one. It's a little bit harder. See if you can sketch this curve. Go ahead, hit the pause button, think about this one. Okay, so x and y are moving around a circle, right? Z, however, is in the xz plane. Notice z equals x squared. So you've got like a parabola thing here. I don't know if this is exactly what you would have. This is x, this is y, and this is z. So you start off here at the point 1, 0, 0, and as you move towards the x-axis, the z-coordinate pi over, oh, I guess that's, oh, it was starting here, wait a second, 1, 0, I don't know if this is the right orientation exactly, but as you're moving around the circle, the z-coordinate is fluctuating between 0 and 1. Oh, this is right. When t equals 0, you're starting off here. Yeah, this is right. At t equals 0, you're at the point 1, 0, 1. And I believe you're moving this way, but you're going down. See that the z coordinate is getting close to 0. Now it's going back up to 1. Now it's getting close to 0. Kind of interesting, isn't it? Anyway, that is kind of tricky. This one, whoops, this one is what we're looking at next. This one, how does it, the z coordinate is 0, and x and y, it looks like a circle, but notice how the radius is always increasing. At t equals 0, you're at the origin. The z coordinate is 0, and as you move around the circle, the radius is always changing, so you get like a spiral effect, see? T equals 0, you get this, and as you're moving around the circle, the radius is getting bigger and bigger. So you're getting a spiral in the xy plane, right? Okay, let's throw this on now. See if you can sketch the graph of this one. Okay, well, you got that spiraling effect, but now z is changing also. So wouldn't this be, as you're moving around, the z coordinate is getting higher too, isn't it? Interesting. All right, now that was so much fun, let's do a couple of different things now. These are hard right here. Suppose you have a line of intersection. I know some students have trouble with this. I want you to find a vector function that that shows the curve of intersection between this is a cylinder and this is a plane. Can you imagine that? An intersection of a plane with a cylinder? Plane with a cylinder? I didn't bother sketching it, but what you could do is this. Since x and y are moving around a circle, couldn't you say x is 2 cosine t, y is 2 sine t? And since z is 1 minus y, you could just say z is 1 minus 2 sine t. So those are the parametric equations for the curve of intersection. And then just put them into the components of the vector function. Sometimes using sine and cosine helps with x and y. Other times you're going to have to try something different. Like in this problem here. Z equals x squared plus y squared. You're supposed to recognize, I guess, that's a paraboloid, isn't it? But notice, you can't use x equals cosine and y equals sine because it's not a circle. Isn't this getting bigger and bigger? So you really aren't. If it were a cylinder, you could, but it's not. It's a paraboloid. So how would you do it? Well, this is one of those times where you might let one of the values be t. Do you see why it would be good to let x be t? Because if x is t, then y would be t squared. And then z would be t squared plus t squared squared, which would be t to the fourth. So that's one way to do it. All right, see if you can try this one. This one's actually pretty hard. See if you can figure out how to parameterize this one. Your temptation might be to let y be t and z 1 minus t, but it turns out you're better off to let x be t, because if you let y be t, how are you going to parameterize x? What you could do, this is kind of sneaky, couldn't you set these two things equal to each other? Couldn't you set the square root of 1, couldn't you set the square root of x squared plus y squared equal to 1 minus y? So when you square both sides, you would get this, right? I would just go like this. I would let this equal 1 minus y. That's what I said. Okay, let the square root of x squared plus y squared equal 1 minus y. If you square both sides, you'll notice that the y squareds cancel. So then you can solve this for y, it turns out. So what does that say? Since you can solve this for y, this is kind of tricky, but what you would do is you would let x be t, y would be 1 minus t squared over 2, and then how do you find z? Well, notice z would be 1 minus y, and since y is this, oh, here we go. This is what I was thinking. Since z is 1 minus y and y is this, then z equals 1 minus this, right? z equals 1 minus this thing. If you simplify that, you end up with 2. Well, you end up with, when you simplify this, you get 1 plus x squared over 2. That's what you get for z. Okay, so that's how I got this. Anyway, that one's kind of hard. Let's see. This one isn't very hard. See if you can do this one. Okay, you should recognize this is a cylinder intersecting a paraboloid. This is a paraboloid that opens down, by the way. My guess, since I've done the problem, I already know the answer, but I would think that the curve intersection would be a circle. Where a cylinder would intersect a paraboloid, I think you could get a circle. So I would let x be cosine t, y equals sine t, and then z would just be 4 minus x squared minus y squared. But if you factor out a negative 1, isn't it just 4 minus 1, which is 3? So there you go. Sure enough, it is a circle that's 3 units up above the xy plane. Well, I guess that's it for now. I'll see you next time. Bye-bye.